Good afternoon, everyone. Thank you so much for joining today's webinar. I'm Ben Monaveri, and I'm delighted to present this overview of the proposed revision to AS5216. Today, we'll explore the key enhancement in the public comment draft, focusing on what these changes mean for engineers and the broader construction industry. This is an exciting development that will significantly impact how we approach fastening design in Australia. Before we begin, I would like to acknowledge that this event is being held on the traditional lands of the original inhabitants and pay my respect to elders past, present, and emerging. Allow me to introduce myself. I'm Ben Monaveri, Hilti, Australia's Codes and Approval Manager. I'm a structural engineer with over 15 years of experience in industry. I've been with Hilti Australia since 2019, and I hold a PhD in structural engineering and a master's degree in earthquake engineering. Before we begin, a few housekeeping reminders. At the bottom right corner of your screen, you will find icons for asking questions and participating in polls. Please feel free to type your questions at any time, and we will address them during the Q&A session at the end of this session. Throughout the session, we will also have poll questions to keep our discussion interactive and engaging. Additionally, this session is being recorded, and you will receive a link to the recording after the webinar. To understand the significance of the AS5216 2025 draft, or the changes, it helps to revisit where we started. Before 2015, Australia had no standardized design requirements for fasteners. Engineers relied primarily on manufacturers' guidance, which created inconsistencies across the industry. This changed dramatically with the formation of AFAC in 2012, a collaboration between Swinburne University and 6 industry partners, including Hilti Australia. Their work resulted in SATS 101 in 2015, Australia's first industry guideline for fastening systems. The momentum continued with AS5216 becoming a full standard in 2018, followed by the inclusion of the National Construction Code in 2019. The 2021 revision added crucial seismic provisions and specifications for post-installed rebar. Now, the 2025 draft builds on this foundation by introducing fatigue design, durability requirements, improved post-install rebar design method, and provisions for power-actuated fasteners. These provisions significantly improve the standard. As discussed, the 2025 revision introduces 4 key enhancements that will transform fastening design practices in Australia. First, we have a new normative framework for fatigue design in Appendix G, addressing a critical gap for infrastructure and machinery applications. Second, mandatory durability design requirements in Section 10 ensure long-term performance considerations. Third, new provisions for power-actuated fasteners in Appendix E, specifically for redundant non-structural systems. Finally, an advanced bond splitting model for post-install rebar in Appendix D, offering significant design efficiencies. Each of these enhancements responds to identified industry needs and aligns Australian practice with international best standards. Let's examine each area in detail. Okay, so before actually going to the next slide, I want to start with a question. This is the first question actually, so you should be able to see it as a pop-up on your screen. The first question is, which AS5216 2025 enhancement are you most interested to learn about in this session? Is it fatigue design framework? Is it durability requirements? Is it about power-actuated fasteners provisions? Or is it about improved post-install rebar design method? There's no right or wrong answer here. I just want to understand what is the most important update in this standard. I will wait a couple of seconds here to see how you want to respond, and then we go to the next slide. Okay. So we go. I don't know. I don't see the answers here, so I will just proceed with this one. Okay, let's begin with fatigue design, a critical consideration for infrastructure, machinery support, and dynamic systems that has been largely overlooked in Australian practice until now. Appendix G introduces the first normative guidance for fatigue design under AS 5216. Previously, AS 5216 2021 contained no normative content for fatigue, and designers relied on AFAC Technical Note 14 as guidance. The 2025 draft fundamentally changes this by formalizing fatigue design requirements. The framework applies to pulsating tension and alternating or pulsating shear actions, but importantly excludes redundant non-structural fasteners, fastening with annual gaps, and shear loading with lever arms. A critical requirement is mandatory pre-qualification to EAD 330250, which is the European assessment document for fatigue testings of post-installed fasteners. It's essential to understand that fatigue represents a distinct loading category. Fatigue is characterized by repeated high-frequency load cycles, typically between 10,000 to 100 million cycles. This distinguishes it fundamentally from seismic actions, which involve fewer cycles, usually between 10 to 10,000 cycles, and shock loads, which involve very few cycles, typically between 1 to 20. Each loading type affects fasteners differently. While seismic loading might cause 100 significant cycles during an earthquake, fatigue involves millions of small amplitude cycles from machinery vibration or traffic loading and so on. This difference in behavior means fatigue must be treated as its own distinct design category with specific testing and design requirements. Okay, next, it's time to the second question. Which loading scenario represents fatigue condition? 50 load cycles during an earthquake, 500,000 cycles from machinery vibration, 5 cycles from wind gust, or single impact from dropped equipment. I guess this is a very easy question, and I'm saying that many of you are responding to the correct, which is the correct option, which is the B. So 500,000 cycles from machinery vibration is a fatigue load. Okay. Fatigue design is built around the SN curve, also known as the Wooler curve. This fundamental relationship shows how load range and the number of load cycles affect resistance. The curve demonstrates that as the number of cycles increases, the allowable load range decreases, eventually like a flattering at what we call it endurance limit. Importantly, designers don't use average values in fatigue design. We use characteristic resistance values, the 5% fractal, and apply safety factors to determine design values. This conservative approach accounts for the statistical nature of fatigue failure and ensures reliability over the structure's service life. Understanding why fatigue-approved anchors are essential requires examining the complexity of post-install fastening systems. These systems include multiple components made from different materials like steel, anchor, chemical bonds, and concrete, each with different fatigue characteristics and different SN curve. The steel component might fail in the bolt, sleeve, or threader section, and failure location can vary across anchor sizes due to different manufacturing processes. On the other hand, the bond component has entirely different fatigue behavior, particularly for chemical anchors. And the base material, which is concrete, adds another layer of complexity because all these components interact as a complete system. Individual component testing cannot predict the overall system performance. This is why fatigue-approved system must be tested as a complete assemblies or as a complete system. And perhaps this is why different anchor systems require separate fatigue qualification, even they appear very similar. Okay. Cyclic loads are categorized into two main types: pulsating and alternating loads. Pulsating loads maintain the same sign throughout each cycle. For example, tension loads that vary from 10 kilonewton to 50 kilonewton but never go to compression. These are common in suspended loads subjects to vibration. On the other hand, alternating loads change sign during each cycle from tension to compression and back again. This might occur in constructions, in connections subject to wind loading or seismic action. The distinction is crucial because alternating loads are generally more damaging to fatigue life. Appendix G includes a simplified design method aligned with Method 2 of EOTA TR061. This approach treats the full applied load as cyclic and checks it against the fatigue endurance limit. While conservative, this practical approach works well when exact load cycle information isn't available, which is often the case in real projects. The design fatigue resistance equals the characteristic fatigue resistance divided by the appropriate safety factor. This ensures adequate safety margins while providing a straightforward design approach that engineers can implement. Okay, it's time to the third question of today's webinar. In the simplified fatigue design method, what percentage of the applied load is considered fatigue relevant? Is it 25%? Is it 50%, 75%, or 100%? I will wait a couple of seconds for your answer. And I feel like I have responded to this question in the last slide. Okay, as I said before, in the simplified method, 100% of the whole load is considered as fatigue relevant, which is, it could be a bit conservative, but that's how the simplified method works. Okay, for a fastener to be used in fatigue design applications, it must undergo rigorous qualification to EAD 330250. However, this isn't a standalone process. The fastener must first meet static qualification requirements, either EAD 330232 for mechanical anchors or EAD 330499 for chemical anchors. Once we have a static qualification, fatigue-specific testing begins. This comprehensive testing program evaluates all potential failure modes under cyclic loading conditions. The resulting European technical assessment contains all the resistance values and reduction factors required for fatigue design calculation. Fatigue design requires verification of all potential failure modes: tension and shear, single anchor and group anchor configurations, and so on. So each failure mode has specific fatigue resistance values and reduction factors that must be applied. It is important to note that fatigue doesn't just affect one failure mode. Steel failure, bond failure, concrete failure all respond differently to cyclic loading. The designer must check all the failure modes. Okay, Hilti currently offers multiple anchor systems qualified for fatigue applications. For chemical anchors, we have HY200R-V3 and RE500-V4. Both provided excellent fatigue performance across a wide range of diameters. For mechanical systems, we offer HDA and HSL4G anchors. These products cover diameters from MA to M24, providing comprehensive solutions for most fatigue applications. Each system has been tested under EAD 330250 and received an ETA, which is European Technical Assessment for fatigue application. Moving to our next major enhancement, durability requirements, which are equally crucial and important for long-term structural performance. Section 10 of the AS 5216-2025 draft introduces a structured approach for assessing long-term fastener performance. Fastener durability is affected by multiple factors that interact in complex ways. Corrosion mechanisms, including atmospheric, galvanic, pitting, and crevice corrosion. Structural factors include creep under sustained loads and dynamic actions like fatigue and seismic loading. Environmental conditions such as moisture, temperature variations, and chemical exposure also play crucial roles. Base material conditions are also important. Concrete cracking, crack cycling, water saturation, and carbonation all affect fastener performance. Finally, disasters like fire or earthquakes can significantly impact durability. The new standard requires designers to systematically assess these factors rather than rely on generic assumptions. The durability assessment framework distinguishes between macro and micro environments. The macro environment includes geographic locations factors covered by AS 4312 corrosivity zones, essentially the broader environmental conditions affecting the structure. However, the microenvironment around each fastener can be quite different. The framework identifies 4 distinct zones: exposed fastener component, the fixture, and any analog gap, intermediate layers such as grout or sealant, and the embedded portion within the base material. Each zone can have different corrosion risk and exposure conditions. For example, the exposed portion might face severe marine conditions, while the embedded portion is protected within concrete. This detailed assessment enables more accurate durability predictions. All right, that's time to the next question. How many distinct microenvironments does AS 5216-2025 identify around each fastener? I also responded to this question in the last slide, but let's see how many of you catch that in the slide. So the first one is A is 2, B is 3, C is 4, and D is 5. I will wait a couple of seconds for you to respond to this question. Okay, as many of you again has responded these questions correctly, not option C is the correct answer. As discussed, the framework identifies 4 distinct zones: exposed fastener, fixture, intermediate layers, and the embedded portion. Okay, so when a specific durability data isn't available in pre-qualification document like ETA, the draft references AFAC Technical Note 15 for guidance. This comprehensive document provides practical approaches for durability assessment. For stainless steel fastener, selection is based on corrosion resistance factor, which is CRF assessment, as outlined in EN 1993-1-4. This systematic approach matches stainless steel grades to a specific corrosion environment or corrosive environments, ensuring appropriate material selection for the intended service life. The standard addresses multiple corrosion mechanisms that can affect fasteners. Environmental corrosion resulting from atmospheric corrosion exposure and varies significantly across Australia's diverse climatic conditions. Bimetallic or contact corrosion occurs when dissimilar metals are in electrical contact. Pitting corrosion creates localized deep penetration, particularly dangerous because it can cause failure with minimal visible indication. Crevice corrosion occurs in confined spaces when oxygen depletion creates aggressive conditions. Hydrogen-assisted cracking affects high-strength hardened fastener material under combined stress and hydrogen exposure. Understanding these mechanisms enable appropriate material selection and protective measures. All right, so it's time to the next question. Which of the following is not a type of corrosion? I will read it again. Which of the following is not a type of corrosion? So it's a bit tricky, this question. I think this is one of the hardest questions that I have asked so far. So it's talking about the type of corrosion. So the first option is bimetallic corrosion. The second one is hydrogen inducing cracking. The third one is non-uniform corrosion, and the last one is stress corrosion cracking. I'll wait a couple of seconds to see if you can guess the correct answer. As I expected, this was a bit a tricky question, but option C is the correct answer, which is it's not a type of corrosion. So non-uniform corrosion is not a type of corrosion. So let's go to the next slide. Okay, AS 4312 provides atmospheric corrosivity zones for Australia based on ISO 9223, offering information on atmospheric corrosivity and corresponding durability for different metals. However, for stainless steel, it references EN 1993-1-4, which provides a more sophisticated approach. This standard addresses stainless steel durability by establishing the corrosiveness of a specific environment and enabling selection of appropriate stainless steel types based on their corrosion resistance. This two-step process ensures optimal material selection for a given service condition. This is the CRC table in effect technical note 15, which categorizes corrosion resistance into 5 levels, CRC1 through CRC5. CRC1 represents low corrosion resistance suitable for mild internal environments, while CRC5 provides high resistance for severe marine or industrial conditions. This systematic approach removes guesswork from stainless steel selection, providing clear guidance on appropriate grades for specific environments and intended service life. Bimetallic corrosion occurs when metals with different electrochemical potentials are in electrical contact in the presence of an electrolyte. The more noble metal becomes the cathode and is protected, while the less noble metal becomes the anode and corrodes first. Critical considerations include the area ratio between the metals. A smaller fastener in contact with a larger structural element creates particularly aggressive conditions for the fastener. The design guidance emphasizes that we need to avoid situations where the fastener is less noble than the fixture, as this accelerates fastener corrosion and can lead to premature failure. Hilti employs both active and passive corrosion protection measures to extend component service life. Active protection includes advanced planning that considers corrosion from the design stage, galvanic separation to prevent bimetallic corrosion, and selection of corrosion resistance materials. Passive protection involves measures that directly affect the component and hinder corrosive medium access. This includes metallic coating like zinc plating, organic coating such as paint systems, duplex system combining multiple coating types, and inorganic coating like phosphating. Material selection between stainless steel and protective coating depends on a specific environment and application requirements, with stainless steel generally preferred for severe or long-term exposure conditions. Okay, now let's examine the new provision for power actuated fasteners in Appendix E, addressing a significant gap in the current standard. Power actuated fasteners represent a complete fastening system, including fasteners, typically nails or threaded studs, a power source, and specialized power actuated tools. The power source varies by technology. Power actuated tools use cartridges, gas actuated tools use pressurized gas cans, and the battery actuated tools use obviously rechargeable battery systems. Each technology has distinct characteristics regarding power output and application suitability. Critical factors for successful installation include proper power adjustment, tool settings, and fastener selection to ensure appropriate penetration in the base material. Incorrect settings can result in either insufficient penetration or excessive penetration that damages the base material and the fixture. Power actuated fasteners fall into two main categories: drive pins and threaded studs. Drive pins feature an enlarged head that directly supports the fixture. The fixture attached via the pin head, making installation quick and efficient for appropriate applications. Threaded studs, on the other hand, extend through the fixture and are secured using nuts and washers similar to conventional bolted connections. This arrangement provides adjustability. The new provisions specifically addresses redundant non-structural systems, a critical concept for power-actuated fastener applications. Non-structural elements are components attached to and supported by the structure, but not contributing to the primary load-resisting system. Redundant systems are statistically indeterminate with at least 3 supports or fixing points. The key characteristic is that the system retains static stability after losing any fixing point. This redundancy principle is crucial for power-actuated fasteners because it acknowledges that individual fasteners might fail without causing system collapse because of the existing redundancy in the design. Okay, so question number 6, what is the minimum number of fixing points required for a redundant system? Is it 2, 3, 4, or 5? I also responded to this question in my last slide. If you remember, I said the minimum required is 3 based on the standard. So option B was the correct answer. Okay, so while AS5116 comprehensively covers cast-in and post-install fasteners, it previously didn't address power-actuated fasteners. The 2025 revision begins to fill this gap with general guidance provided in the standard and detailed information available in AFAC Technical Note 11. This development recognizes the widespread use of power-actuated fasteners, or PAF, in construction and the need for standardized design approaches to ensure safe and reliable performance. For safety-critical applications, power-actuated fasteners must have current pre-qualification documents such as European Technical Assessment, which is ETA. Design must incorporate planned redundancy following the redundant design principles established in AS 5216. This approach ensures that even in safety-critical applications, power-actuated fasteners can be used safely provided appropriate redundancy and if qualification requirements are met. I'm excited to highlight that Hilti XX seismic nail, or seismic pin, the world's first nail tested and approved system for seismic conditions. XX nail features several groundbreaking characteristics. The patented helix tip design rotates during installation, screwing the pin into concrete rather than simply being driven, which provides up to 50% higher tension capacity in cracked concrete compared to conventional power-actuated fasteners or systems or nails. The letter X on the nail head ensures proper identification and inspection, crucial for seismic applications. And most importantly, this system provides a safer and 4 times more productive solution than current method. With limited exposure to dust and hazardous substances and reduced fatigue when working overhead. This innovation demonstrates how power-active fasteners can evolve to meet demanding performance requirements while improving installation safety and efficiency. Finally, let's examine the enhanced provisions for post-install reinforcing bar connections, perhaps the most significant technical advancement in the AS 1516 revision. Understanding post-install rebar requires distinguishing it from chemical fasteners. Chemical fasteners connect a steel fixture to concrete, with the anchor taking up both tension and shear loads directly. The interface surface roughness doesn't significantly affect performance. Post-install rebar, on the other hand, connects two concrete members, existing and new construction. Shear forces transfer through friction over the interface surface area, making interface roughness critical. The post-install rebar acts primarily in tension, connecting the concrete section rather than supporting attached fixture. This fundamental difference requires different design approaches and failure modes considerations. The failure modes for chemical fasteners include steel failure, pull-out failure, splitting failure, and concrete breakout failure. But in rebar model, we only have a steel failure, pull-out failure, and splitting failure modes. In this model, concrete breakout is restrained and doesn't develop. So that's the only difference between these two methods. Current post-install rebar design in AS 1516 2021 Appendix D links to AS 3600 2018 Section 13, which covers a stress development of reinforcement. However, AS 3600 doesn't contain specific provisions for post-install rebar applications, requiring designers to make conservative assumptions that often result in long embeddment depth. The current equal to casting approach assumes that post-install rebar performs identically to casting reinforcement. While conservative, this approach has significant limitations. Bond strength of, as an example, of RE500V4 chemical anchor can achieve up to 14 MPa. However, AS1516 limits the usable bond strength to match casting bar allowable values, which is typically around 2 to 4 MPa, depending on the concrete strength. So obviously, we're not utilizing the full capacity of the chemical in our post-install rebar connections. This conservative approach often results in deep embeddment depth, which are impractical for many applications and don't utilize the superior bond characteristics of chemical anchors. The improved bond splitting model represents a fundamental advancement. While equal to casting design requires deep embeddment depth for achieving steel yielding, the new model recognizes superior chemical bond characteristics and permits reduced embeddment depth. However, reduced embeddment depth creates a potential for concrete cone failure, which must be checked in the new design method. The equal to cast-in approach embeds so deeply that concrete cone failure is unlikely, but the improved method requires verification that concrete cone failure doesn't govern the design. So if I go back to the first slide, so in equal to casting, we assume we have a linear relationship between the embeddment depth and the maximum or the capacity of the post-install rebar or cast-in rebar. So this is a method equal to cast-in. As you can see here, this is a linear relationship. And if you want to design for yield, which is the blue line, we need to drill to this depth. But within the new design method, because we are utilizing the higher bond capacity of the chemical, we are having higher capacity, but as you can see here, is not a linear relationship anymore. So So if we want to design for the same yielding capacity or yielding of the bar, so instead of drilling to this depth, we are reducing the embeddment depth to this depth. But because we have reduced embeddment depth, we're not sure if the concrete cone failure is governing or not. So that's why we have to, in this design method, we also need to check the this design method. Okay. So it's time to the last question of this webinar. So what failure mode needs to be checked in improved failure post-install rebar design method in comparison to equal to cast-in design method? Steel failure, bond failure, concrete breakout failure, or splitting failure? And I think I responded to this question in the last slide as well. But we'll wait a couple of seconds for you guys to respond, and I will continue. Perfect. Okay. So as most of you have answered this question correctly, the option C is the correct answer because the new design method results in less embeddment depth. Concrete cone failure also needs to be checked. 3 distinct post-install connection types now exist, each with different design method and qualification requirements. Chemical fasteners follow AS 5216 section 6 and 7 with EAD 330499 qualification. And then the product has a different ETA based on this EAD. So equal to cast-in post-install rebar uses AS 5216 Appendix D plus AS 3600 section 13 with a different EAD, and it has a different ETA. And the new cast-in post-install design method, which is the beyond cast-in design method, utilizes the enhanced design method in AS 5216 2025 revision with a new EAD qualification, which requires another ETA. So as an example, in this case, for RE500V4 that has been approved for this system, we have 3 different ETAs because it has been approved for different applications. So it can be used as a mechanical, as a chemical anchor. It can be used as a post-install rebar with the equal to casting rebar design method, or it can be used for the exact, again, for rebar applications, post-install rebar applications with the beyond casting, the new design method in AS516. Okay, the improved bond splitting model accounts for actual stress distribution in the length of the bar. Equal to casting assumes uniform bond stress distribution, but in the improved model, the bond stress varies with concrete cover and in depth. With high concrete cover, both design methods show increased capacity, but the improved model continues gaining capacity. Similarly, the improved model shows varying bond strength with embeddment depth, reflecting actual load distribution behavior rather than a constant relationship assumed in equal to casting system. So if I show you here, so this is equal to casting graph. So this is look at how the capacity changes in embeddment depth. This is a bond strength. So the bond strength in equal to casting system is constant. It doesn't really matter on the embeddment depth. But as you can see here, with the new design method, we start with a much higher capacity. And as we go deeper into concrete, we have less capacity. And then this also changes with the confinement. Confinement is the concrete cover or the half of the space between 2 bars. So as the more confinement we have higher capacity, and it's going to be flat out at some area here. So previously, for example, for RE500V4, for let's say for a specific size, we used to say it has 10 MPa, 2.5 MPa, or a constant value. But as you can see here, we have a new equation. So for the bond strength is not a constant value anymore. So it depends on the embeddment depth. It also depends on the concrete cover. We have to calculate how much capacity we have in different depth. So it's a very hard calculations if we want to do by calculation, but obviously with process engineering software, we can do it automatically with ease. Okay. Next slide. Currently, 2 Hilti chemical anchors are qualified for the improved bond splitting failure. The first one is RF500V4, and the second one is HY200RV3. These anchors have undergone extensive testings to EAD 3302402 and received European Technical Assessment, which is ETA, specifically for beyond casting performance. Importantly, chemical anchors are not interchangeable in this design method, because each chemical has unique characteristics and load distribution properties, which can be achieved or being derived through testings. Okay, so let me show you a couple of examples. Actually, there are 2 examples. The first example, we have a slab to wall connection with a specific loading conditions in 30 MPa concrete. Using the standard AS3600 design method, which is equal to cast in, we need approximately 650 mils in depth, which often is impossible in typical wall constructions. And then if we go to HY200V3 as an example, reduce depth to 250 mils. And if we use RF500V4 in this example, we achieve 195 mil depth, which is in this example, we are achieving 70% reduction in depth, transforming impossible connection into a practical solution while maintaining structural integrity and safety margins. Let's go to the second example. The second example demonstrates a column to foundation connection. A standard equal to casting design requires 661 mil depth. If we change to RF500V4, then depth will be reduced to about 453 mils. And if you go to HY200V3, now we achieve to 330 mil depth, which is a 50% reduction. As you can see here in this example, HY200 gave us a better result because this is a different design, and specifically it's because we have a different confinement. So with different confinement, either RF500 or HY200 can give us a better result. So in your design, I suggest to check which one gives you a better capacity, if it's possible to use HY200, because it's a fast cure epoxy. So for long depth, especially for rebar applications, I would suggest to go with RF500V4 because it's a slow cure epoxy and it gives you more time to inject the chemical and install the rebar. So this is a 50% reduction. So this represents substantial cost saving, reduced drilling time, improved construction safety, and enhanced sustainability through reduced material usage and construction impact. So it's not just about saving on the epoxy, also in the construction, the installation, and everything is going to be saved as well. Okay. So we got to the Q&A session. So we hope you found the webinar informative. We'll now take your questions, and haven't been addressed during the webinar, please feel free to type your questions in the question tab. Okay. So I've got a couple of questions here. So I will try to answer a couple of those ones and see if you've got more time to go through all of them. So the first question, so do we need to redesign existing anchor systems if the new FATIC provisions becomes mandatory? That's a very good question. The short answer is not necessarily. If an anchor system was designed under AS56 in 2021 or an earlier edition, and FATIC design was not required at the time, there's typically no obligation to redesign it. Once even once AS5016 2025 is published, it won't be mandatory until it is referenced in the National Construction Code. But please note that following the latest standard is usually considered the best practice. Doing so is not legally required unless the NCC mandates it. For new projects submitted after AS5016 2025 revision becomes the NCC reference standard, the fatigue provisions in Appendix G will apply where fatigue loading is relevant. So in summary, existing designs approved under an earlier standard generally remain compliant, but new applications involving fatigue loads should align with the latest requirements once those requirements are formally adopted into the NCC. I hope that I could answer your question. Let me see if there's any other questions here. I can see a couple of questions that is similar, so I would try to skip those ones and try to capture the ones that is a bit different. Okay, so I think this is a very good question. So question 2, how do I know when fatigue design is required? Again, it's fatigue. So it's a very good question, to be honest. So the draft standard provision provides quantitative fatigue triggers. Fatigue verification is required if you expect more than 1,000 pulsating tension load cycles or more than 100 alternating or pulsating shear loads or cyclic loads, or if the stress fluctuations exceed 100 MPa in tension or 60 MPa in shear due to functional conditions. If any of these thresholds are likely to be exceeded, fatigue must be considered. So, I mean, if it wasn't clear, please feel free to read this standard. I think it's been there, so you can just reference to that one. Going to the next question. It's about post-install rebar design method. Okay, so the new post-install rebar design method sounds promising. Yeah. Why should I use the bond splitting model instead of traditional lap lap length design? I hope I could read through. The improved bond splitting model is specifically beneficial when embeddment depth is constrained or when higher bond strength is needed without increasing the drilling. Unlike the equal to casting method, the new method uses a variable distribution derived from testing to EAD. So it allows more accurate and often shorter movement depth for the same performance, but only if the system is pre-qualified with this behavior, right? So you have to use a chemical anchor that has been tested for this design method. It's ideal for retrofit, precast, and congested applications. Please note this new design method can only be used for end anchorages. So for example, it cannot be used for lap splices. It makes sense. Going to the next question. I have another question for post-install rebar design method. So the question here is, what is the maximum reduced embeddment depth allowed in the new enhanced post-install rebar design method? It's a very good question. I mean, while the new design method allows the embeddment depth to be reduced based on concrete geometry and spacing, there's still a lower limit you must consider. According to Appendix D of the standard, the minimum anchorage length cannot be less than the maximum of 30% of the basic development length, which is based on AS 3600, 10 times the after the bar, and 100 meters. So even if you calculate embedment depth is less than either of these values, we have to limit the minimum depth to these values, which acts as a safeguard to ensure a structural reliability under tensile load. I guess it's a practical balance between optimized design and structural safety. I'm just trying to see if there's any other questions here. Okay, so there is one question here says asking about the fatigue. So why it didn't include the M30 for fatigue? So it's all about testing. So what we have tested and what has been approved. So if we have any specific application that requires like a bigger size of the anchor, so maybe we have some data or we have some testing that we can share with you. So please reach out to us, to one of our engineers, support teams, and then they can share with you some more information, hopefully. Next question. I think I responded most of the questions here. So if I have missed any questions here, please reach out. I guess we can close today's webinars now. So if you have asked any question that I haven't received, if you haven't received any response, please reach out to us, or one of our engineers will contact you to discuss your inquiry. So try to respond. Most of the questions, I might have missed some, so there are a lot of questions, to be honest. I cannot answer all of them here. Hopefully that the webinar was helpful, and yeah, so till next webinar, have a great one. Thank you.